Hi class, welcome to the next section in chapter 5. Today we're going to talk about applications of the derivative in the sciences. So we're going to go through a few of the different sciences and talk about how we use derivatives there. Please remember that derivatives are our instantaneous rate of change, right? So we're just going to talk about how we talk about change in the different sciences and some of their uses for modeling. So let's start off with economics. Okay, so economics is all about money, basically, right? How to manage and spend money for the economy, for a country, for a city, for a company, things like that, right? So we generally like to talk about things like cost, revenue, profit, things like that. That's all sort of self-contained in the study of economics. So we're going to start off with what is called the cost function, right? We'll call it C of Q. Now, if you're not familiar with economics at all, the cost function represents how much it costs to produce a product, basically, right? So if I'm making cupcakes, I have to buy all of the ingredients for the cupcakes. I have to think about how much time I need to invest in making those cupcakes and how much my time is worth, or an employee's time is worth, how much it costs to run the gas or electricity for the oven that I'm cooking it in. All of those costs come into play, right? So your cost function represents the total cost of everything for producing a product, okay? So generally what happens is that I can say, if I have a cost function, I can say, hey, if I make only one of these things, how much does it cost? If I have 100 of these things, how much does it cost? Right? So your cost function should be able to take in an input where Q is the quantity of the amount of product that you want to make. Okay. The revenue function talks about how much money you are going to generate from selling your product. Okay. Now, your revenue function has nothing to do with cost. Right? It does not take into consideration how much it costs to produce something. It's just how much money are you going to make after you sell everything. So you're not deducting from that your cost, your labor, or anything else. It's just how much money do you have after everything is gone, or if you sell Q items. Okay, so we call our revenue function R, right? C for cost, R for revenue. Q is the number of products. So if I sell one cupcake, how much money do I get for selling one cupcake? If I sell 100 cupcakes, how much money will I generate? Okay, so that's your revenue function. Your price function is a little bit different. Okay, so we call price function little p of q. We also call this the demand function, right? So it really represents to us how much we are generally going to sell, right? What is the demand of our product? So it's the price per unit for selling Q units of a product. Okay, so generally the price per unit decreases as the number of units being sold increases, right? So think about when you're going shopping at Safeway versus when you go shopping at Costco. If you're not in this country, consider it as the difference between buying one item versus buying 100 items. Generally, when you buy a lot of things, it's a lot cheaper, right? When you buy in bulk than when it is if you were to buy only one item. So that's what our price function represents. It's the price per unit, right? So if I'm buying 100 cupcakes, it'll cost me less per cupcake than it does when I have to buy just one cupcake. Okay. So my revenue is generated by my price function, right? How much does it cost per item times the quantity of items I'm going to buy. Okay. Represent that as R of Q is just Q times my price function. Okay, my profit function is going to be how much money I make minus the cost that it minus the cost for making that amount of product. Okay, so large P is for profit, little p is for price. So this is the money that's left over after I consider all of my costs, right? So my profit is my revenue minus my cost. Now, if my cost is more than my revenue, then that's when you are losing money, right? So your profit is R of Q minus C of Q. Okay, if I substitute what R of Q is, because sometimes you're given a price function instead of a revenue function. If I'm given a price function, then I can substitute it and consider it as Q times P of Q minus large C of Q. So remember, this little p here is the name of the function. It is not a variable. Okay, Q is your quantity. It's the input. So you have your quantity times your price function minus your cost function for your profit. Marginal cost is the derivative of the cost function. Okay, so we call this C prime of Q. This is the amount, approximately the same amount as the cost of producing one more unit of a product after Q units have already been produced, right? So if I make 100 cupcakes, my marginal cost will tell me how much does it cost for me to make just one more cupcake. So if I've already made 100 and I want to make my 101st, how much is that one extra going to cost me? Now, it's not going to cost me the same as it would to produce just one, because I've already paid for all of the materials for making 100 cupcakes. Maybe I have some left over, or there's different situations that are going to occur. So generally, making just one more is not the same as making just one, right? So this is approximately equal to basically the difference in the cost, right? So if I'm making one more minus how many I've made up to date, it's approximately equal to the derivative of the cost function. Okay, so it's the rate that the cost is changing, right? My marginal revenue, basically the same thing, but it has to do with revenue. So how much money am I generating if I'm gonna sell just one more cupcake, right? My marginal profit is the same thing. If I sell just one more, how much is my price increasing from selling just one more cupcake, right? Etc., etc. So my maximum or minimum of profit is going to occur when my marginal cost and marginal revenue are equal. Okay, now don't confuse this with the cost and the revenue functions being equal. Okay, because when the cost and when revenue are equal, you have no profit, right? Here we're talking about the change in cost and the change in revenue. When the change in cost and the change in revenue are the same, that's when I have a maximum or a minimum value, because I'm no longer increasing my amount of profit. The difference between, right, cost is no longer increasing and my revenue is no longer increasing. So if the amount of money I'm generating is not increasing and the cost is not increasing, then that means I'm at a maximum value, right? So that's when I have a maximum profit or a minimum profit. So the derivative of my profit function equaling 0 is when I'm going to have a max or min, right? As we've seen before, because that's when the tangent is 0, has the slope of 0, I should say. So what this means is, remember what the profit function is. The profit function is revenue minus cost. Okay, revenue minus cost. So if the derivative of this is 0, the derivative of profit is the derivative of revenue and the derivative of cost, right? So again, a maximum or minimum value for my profit means that the derivative is 0. That means that this is 0 because this is the derivative of my profit. And if I solve this by just moving one to the other side, well, that means that the change in my revenue and the change in my cost are equal, right? So here we showed it mathematically. Here we try to explain this verbally for you guys a little bit. So let's just go ahead and do an example. So let's say that we have a price function, okay, little p here for price function. So it's the demand function. The daily demand for coffee at the campus coffee shop can be approximated by this function, right? So square root of 25 minus 0.1 times Q, Q being the quantity being sold, okay? P of Q is the price in dollars, and Q is the number of cups of coffee demanded, right? So if we sell, I don't know, say 1,000 cups a day, well, then that'll tell me my price per cup, right? So the cost function for the coffee shop can be approximated then by C of Q, which is 120 plus 0.75 Q. So again, I'm giving you the price function and I'm giving you the cost function, right? Here, see if Q is the cost in dollars to produce Q cups of coffee, right? So this is how much it costs to produce Q number of cups of coffee, and then this is the price per cup, okay? So if demand is currently 120 cups of coffee per day, we want to find the approximate profit from selling one more cup, okay? So I already sell 120 cups, so what happens if I sell one more at the end of the day? So let's think about this a little bit, right? If I sell one cup of coffee, just only one cup of coffee, I make a certain amount of money. If I sell 2 cups of coffee, I've doubled the amount of money of revenue profit that I've made, right? Because I sold twice as much. But if I've already sold 120 cups of coffee, selling one more doesn't add a lot of money to my profit amount, because I've already sold a lot. So one compared to the 120 I've sold already is not going to increase my profit by a whole lot, right? So that's kind of what we're getting at here for the marginal cost or the marginal profit is, if I sold one more, how much extra money am I going to be making, right? Like, how is that increasing my profit amount? And that's what we're doing here right now. So using the functions that we had before, okay, I first have to find, so I'm looking for profit. So I need my revenue because I already have my cost, right? I know that revenue is going to be my price function times Q, right? If revenue is not given to me, then Q times my price function will give me my revenue function. So we're going to find my revenue function. Okay, I know what my profit function is. I have cost. I need to figure out my revenue generated before I can talk about profit. So Q times P times Q will give me a profit function of this, which we already know. We've seen that before. So if I substitute in my functions, I have Q times P of Q minus my cost function, right? Again, make sure you throw that in parentheses so that we can distribute this negative sign later. So we can simplify from here if we want. It's not super necessary for us to do so, but we can. But really my goal is just figure, well, this is my profit function. So I need to find the marginal profit. So I really just need to differentiate this, okay? So here I simplify, just putting things in order, distribute this negative sign, and then we'll take the derivative. So remember, our input value is Q, so that is our independent variable. So we're differentiating everything with respect to Q. So that means here I will use the product rule. Here this just goes to negative 0.75 and the 120 will just disappear. Okay, so I got Q times the derivative of Q, times my profit function, which stays the same. I will add to that Q times the derivative of square root 25 minus 0.1 Q. So here we have the product rule. So I have this negative 1/2, and then I decrease the power by 1, and then I take the derivative of the inside function, and I'll add to that this negative 0.75. Okay, and obviously this looks terrible, right? This is a huge mess. So we want to do more math with this, so we want to simplify this. Okay, so we do have what it is that we're looking for. We're looking for the marginality. Okay, so the demand was 120 cups. So as is, we could just plug in 120 into this and see what we get out. Obviously, I like to clean some stuff up. Okay, because what if I ask you to do more with this than later? So I'm just going to kind of put some fractions in here because you guys know that I like fractions and I don't like decimals. So I'm just going to clean it up a little bit. Here I have this negative 1/10 times 120. So that's why we have a minus 120 now in the front. This is very obviously 3/4. Really, I should write this as 1/10, but I'll keep it the same as for right now. But I do have a common term that I can pull out and factor a little bit. Okay, so I'm going to pull out this 25 minus 0.1 Q to the negative 1/2, which bumps this one up to a whole. So I have 25 minus 1/10 to the Q. This one I have the 120Q that's left over, okay? And then this one I have to pull out an extra so it actually gets a 1/2 here, right? So if I'm subtracting a negative, because I'm pulling it out exponent-wise, then it gives me a positive value, which is fine because look here, I get to simplify this. It just makes it a little bit nicer. Okay, not a whole lot, but I can also pull out a 20, a factor of 20, to make these not have any more fractions on the inside, which it looks like I don't do, but normally that's what I would have done, right? So that would bump this up to what's that, 500, right? This would just be a 3, and this would be a 150, I believe, right? No, this would be a 15. Okay, but it's not super necessary. I just wanted to clean it up a little bit. I'm going to plug in 120 anyway, so in all honesty, I could have just plugged in 120 all the way at the beginning here, and it would have been fine. So I'm plugging in 120, throw it in the calculator, and I get 1.191450687, which means that pretty much I'm just making an extra $1.20 from selling one more cup of coffee after I've already sold 120. So that's approximately how much more I'm making. It's also the rate at which my profit is changing, right? So it's increasing slightly, right? So again, so we'll make around $1.19 if I sell an extra cup of coffee above our demand. So let's go ahead and compare this with what I said this is equal to, right? So we said it's pretty much the same as taking my cost of selling one more and subtracting the cost of where I'm at, right? So here I'm looking at profit. So what I'm going to do is I'm going to look at the profit for 120 cups sold for my profit function, which is this, right? So I'm going to plug in 121, and I'll subtract from that 120. So that'll tell me the change in profit for selling one more cup, and I'll compare that to this derivative that I just found. That gave me a value, a marginal profit cost of $1.19, right? So here I'm going to plug in 120 into my 21 into my profit, subtract from that 120. So I just know how much am I making from one more cup of coffee at this point in time. Long calculation, which is fine, right? We're just going to plug it in the calculator anyways. Okay, and we get this. When I subtract these, it is very close, right? So here my marginal profit is $1.19. Here the difference is $1.17. So it's not the exact amount. Again, this is an approximation, right? This marginality is always an approximating. What it is telling me is how my profit is changing at this point in time, right? At this point of sale, right? So the error is pretty small, okay? Around 2 cents, okay? Which isn't too bad. So less than 2 cents. So we talked about marginality a little bit, okay? Which is what we talked about in the beginning, but we haven't talked about max profit yet. So let's talk about the maximum profit I can receive and how many cups do I need to sell in order to make the most money, right? So I want to know when my derivative for profit is 0. Okay, so we had this function here, which is one of the reasons why it was nice to zero it out. If you notice, this is a negative exponent. So whenever this term here is 0, that's when my function is 0. I don't need this term to be 0, because if this is 0, it's in a numerator position, even though it's not written as such. That would make my function undefined. So I really want to know when is this thing 0. Okay. So I'm going to take the inside, I'm going to set it to 0, and I'm just going to start to solve, right? So here, it doesn't look like I did anything from one line to the next. It happens every so often. So I'll go back and fix that. But like I said before, I'm going to clear out these denominators, okay? So I'll just multiply everything by 20. Then I want to start moving stuff around. Really, I want to isolate Q, right? So in order to get Q alone, I need to get rid of the square root sign, so I'm going to move everything to one side and then square both sides. Okay, so I move everything to one side. Here, I'll divide by 15, or I'll keep it. It doesn't really matter. But I do prefer to divide, so divide everything by 15, square both sides. So this turns into 25 minus 0.1q. Here, this will be squared. I don't always have to expand everything. I know it's a math class, but I like to just work with stuff rather than calculating a bunch of things, right? So I'll just square it and then I'll isolate my q, right? So I do have to multiply it out. I'll set it equal to 0. I get to combine my like terms, right? So my two q's here and my constant terms. Okay, but first I clear out, what did I do? So it looks like okay, so I'm clearing out fractions slowly, right? So first I multiplied everything by 9. Okay, multiply everything by 9 to get rid of the 9 and the 3. Next I will multiply everything by 50. Okay, because that's a common denominator between 10 and 25, so I multiply everything by 50 after that. Now I can add things together. Okay, and the reason I do this is just to get rid of the fractions. So now I can plug everything into my calculator, use the quadratic formula. Okay, simplify that down, and I get my two answers. So I have a maximum profit at one of these values, okay, or at both of these values, right? One of these possibly is extraneous, meaning that it's not necessary. Maybe it's a minimum instead of a maximum, or maybe it's just some extra thing that doesn't actually work with my function, right? So again, my original function was a square root function, right? Which means I really should have only one solution to this square root problem that I have here. Okay, highest power is 1/2, or actually highest power is just 1. So if I'm getting two solutions, that means that I probably have an extra solution because of the fundamental theorem of algebra, right? Fundamental theorem of algebra, which we covered way back in chapter 1, says that the highest degree of your polynomial tells you how many solutions you have. The highest degree was 1, so I should have really only one solution, which means one of these solutions is extraneous. So my practical domain is 0 to 250, okay, because of what I'm allowed to plug in here, right, to the square root. I cannot have the square root be negative. So if I set this equal to 0 and solve, that's 25 over 0.1 or 250, okay, which both of these values is within that domain. So sometimes you could just try to find the domain for your function, and that'll kind of kick out one of your possible answers right away. Here for my practical domain, both of those answers are in there, so that doesn't help. Okay, so then what I'm going to do is I'm going to look at the values at each end. I'm going to look at 0, I'm going to look at 250, I'm going to look at 150, and I'm going to look at 179.9. And out of all of those four, one of them is going to be a maximum, right? So when I plug in 0, I get out negative 120. When I plug in the next value, I get 241. So again, this is for profit, right? So 0 gives me a negative profit because it didn't generate any money. Looking at 150, I make $241. Looking at 179, I make 221, which is less than at 150. And if I look at the end, the 250, the largest value I'm allowed to plug in into my domain, I'm losing money. Okay. So my max profit then is $241.86, and that happens when the coffee shop sells 150.9 cups of coffee. So we'll round that up to 151 cups. Okay. So now let's look at physics. For physics, we have lots and lots and lots of applications of the derivative, but we'll stick to the most common one, which is modeling motion. We talked about this a little bit, so we'll just go into a little bit more depth at this point, since we're talking about the different applications. So let's say that we have a position function, which we call s of t. So s of t models the position of an object at time t. Then the derivative of this position function, as we know, is the velocity function, which we call v of t, the velocity at time t. Okay. The second derivative of our position, which is the first derivative of velocity, is our acceleration function. It tells us how fast our object is accelerating at time t. Okay. These three functions are extremely important, right? The position, the velocity, and acceleration. These are literally how we send a rover onto Mars, right? Is these three functions. Okay. So they are very important for us. They're used to model everything, all of your video games, all of the safety features in your car, all of the roller coaster rides you like to go on. Literally almost everything that we do as people is modeled and analyzed using position, velocity, and acceleration. Okay, so again, especially in physics. So this allows us to do lots of things, as I just mentioned, right? So there are higher derivatives. I did talk about them very briefly in chapter 3, I believe. And so the higher level derivatives are used. They're used in cars. They are used when we're trying to create roller coasters and things like that. They are the third derivative is called jerk. Okay, it's the rapid increase in acceleration or deceleration that causes your head or body to jerk, right? So again, remember what we're talking about. We're talking about rate of change, right? Velocity is the rate of change of your position. It's how you're moving through time, right? How are you moving faster or slower as time progresses? Your acceleration is how your velocity is changing. If your velocity is increasing in speed, then you are accelerating, right? If your velocity is decreased in time, then you are decelerating. So that's what acceleration is. The rate at which you accelerate or the rate at which you decelerate is your jerk. It's called your jerk, right? So if you accelerate quickly, then that's a jerking motion, right? This third derivative of position is jerk. The fourth, fifth, and sixth, I know we haven't really seen these notations too much, but after the third derivative, we just write in parentheses 4, 5, or 6. This is not power, right? Power would be on the outside of the entire function. When you see 4, 5, and 6 like this, or any other value, that's a derivative term, because you lose track if you write too many tick marks. Imagine if I had 6 tick marks here. You'd have no idea what it was that you're looking at. So we write after 3, we write 4, 5, 6, 7, 8, 9, 103, whatever it is. So the fourth, fifth, and sixth derivatives of position are called literally snap, crackle, and pop, right? Which is like the cereal, right? Like Rice Krispie treats. So snap, crackle, and pop, respectively. So let's do an example. Okay, so let's say that the movement of a particle can be modeled with this third degree polynomial. Okay, then the velocity of this particle is given by the derivative, which is 3/2 x squared minus 6x plus 11 over 2. The acceleration is the second derivative, which is 3x minus 6. Okay, so here, this is my position. Okay, this models my position over time. So as time moves along, this can represent distance. This can represent height. This can represent all kinds of outputs, right? As time progresses. My first derivative, my velocity, shows here I'm increasing, right? So I have a positive velocity, and here I'm decreasing in whatever output this represents, which represents me being negative, and then I start to increase again. So the rate of change, the slopes here, begin to be positive, more and more positive as time goes forward. My third derivative, oh, sorry, before we do that. So notice that I have maximum values here and min values here, and that's when my tangent line is 0, right? So when the tangent line is 0, my derivative function is 0. That is when I have a local maximum and a local minimal value, okay? Here my second derivative is just a linear function. You notice that for my second derivative, when it has a horizontal tangent line of slope that has 0, my third derivative is also 0 as well. Okay. So now let's move on to biology. We're not going to go through all the sciences. I believe this might be the last one that we go through. But this is just, giving you guys a nice view of how we talk about rate of change and why it's important for us. Okay. So for this example, let's say that the number of yeast cells in a lab culture increases rapidly initially, but then eventually it levels off, right? The population is modeled by the given function, n equals f of t, where f of t is a over 1 plus b e to the negative 0.7t. So if you think about this, what happens as t goes to infinity, this whole thing here basically goes to 0, and you're kind of left with just a over 1, right? So it levels off at a, but initially it's going to increase very, very quickly. Okay. So here t is measured in hours. At time equals 0, the population is 20, and it's increasing at a rate of 12 cells per hour. We want to find the values of a and b, right? So we have some information here. A and b are unknown to us, but we're given some values. So they're asking us to find a and b given the information that we have, right? That when t equals 0, we have an output of 20, and the rate of increase is 12 cells per hour. So according to this model, we want to know what happens to the yeast population in the long run, which we actually kind of just talked about, right? Because it says it levels off, and informally I talked about that, hey, it looks like it goes to a, but I don't know what a is. So what value does it level off to? So if I plug in 0, I get out 20. Okay, that's a piece of information that was given to me. So I get this equation. I can't solve for a or b specifically yet, but I can say a equals this in terms of b. So that will be helpful. And I can rewrite my function in this form, okay, so that I can just use the chain rule, or I can keep it like it is here and use the quotient rule. It's kind of up to you at this point. But its derivative will be found like this if I use the chain rule, right? So this negative 1 comes to the outside, I get a negative a. The negative 1 reduces down to negative 2. The inside function stays the same. Then I take the derivative of the inside function, so I get the negative 0.7 b e to negative 0.7 t. Okay, I can simplify from here if I want to. Actually, there's not really much to simplify, so I kind of leave it alone. I do know that the derivative at 0 is 12. I'm increasing, so it's a positive 12 when time is 0. So I plug this into the derivative, so I will get 12 out when I plug in 0 for t. Okay, so I get 1 plus b. I get negative 0.7 b. So now I have two equations. I have this first one here from my point 0 and 20, and then I have this equation from 0 and 20 in my derivative. Okay, so that gives a system of equations, which I then have to solve. There's not really an easier way than another to solve for this, but I can, right? So I need to solve. I would multiply both sides by 1 plus b here, so I can try to put it in a form that's nice for me to look at, and then just make a substitution. Okay, so here's what I would have if I did that. Here, remember, this is a denominator function because it's negative, so I can multiply that on both sides as well. So I have 12 times 1 plus b squared. Okay, 12 from 1 minus b. When I move it over, this negative 2 turns to a positive 2. And this times 1 plus b gives me my 20 plus 20b. Okay, I still have this b here that's left over, and this a, and the two negatives make it positive. So that's how we get this system of equations. A little bit nicer to look at. I know what a is equal to, so I probably just want to substitute that in for my a. That way I have everything in terms of b. Okay, and then just start solving, right? So I have something that's quadratic in nature, so I want to zero this out, multiply everything out, right? I'm going to multiply this through by b. I'm getting rid of my fractions, so I multiply everything by 10. Okay, and so from here, I will start to distribute everything, right? So I'm going to expand this term now, and I will distribute this b. Okay, so I distribute this b. I expand this term, and then now notice that yeah, I multiplied everything by 10, but now everything is a multiple of 20. So I'm going to divide everything by 20 just to bring my numbers down. So I'm not working with very large values. Okay. So now I got 6b squared plus 2b plus 1. This turns into 7b, and this is 7b squared. So next I want to distribute my 6 and start to zero things out, right? I want to get this to be quadratic in nature. So the 6b squared, when I subtract it over, I get just 1, right? I have 12b's. When I subtract it over, I have minus 5. And then I move over this negative 6. So now I just factor, okay? And I know what my zeros are. So I have 2 zeros, negative 1, and 6. So which one of these do I have to use? It's possible I have two answers because look, this is a cubic. But I want to check, just like earlier, if we look at my possible domain, I don't really have any issues here, right? Because this is never going to be negative. So there's no restrictions on B, there's no restrictions on A. So I don't have to use the method of looking at the practical domain. So I'm just going to look at both values. I'm going to plug in B and I'll plug in A, right? So I'll start with B as negative 1. When I do this, depending on, this form of my system of equations, and this form is okay as well. I can also just plug it into here and see what works, right? So I'm solving for the system, so I want to plug it into my system, really is what I really want to use. So if B equals negative 1, then when I plug in 0 and get out 20, I get out A over 1 plus negative 1, which gives me a value that's undefined. Okay, because remember 0 and 20 was the value that I used. So using this form, right, the first part of my system of equations, okay, if I plug in negative 1 for B, this first equation here is undefined on the bottom, which is not okay, right? So that tells me then that B has to be 6. Let's just check it just to make sure. When I plug it in, I'm going to get A over 7 equals 20, which means I can now solve for A. A is 140, which tells me that my equation is 140 over 1 plus 6e to the negative 0.7t. My long run behavior here, I look at what happens when t goes to infinity, and I get out my value of A, which was 140.